Now, in this next example, we're going to look at solids with holes. Basically, let R be a region enclosed by the curves y equals x and y equals x squared. If R is rotated about the x-axis, find the volume of the resulting solid. Now, how this differs from our previous examples is that when you rotate, you're only rotating this particular region, which means every slice has a hole. So you're only interested in this particular region here. And out of that, the inner region is contributed by y equals x squared, and the outer region is contributed by y equals x. So a few preliminary concepts that we need to figure out here. First of all, we need our endpoints. Okay, so endpoints, for the endpoints we solve. When is x squared equal to x? Subtract x to get 0, x minus 1 equals 0. So I get x equals 0 and x equals 1. So that's x equals 0 right here, and that is x equals 1. So that gives me the limits for my integration. The second idea is that, for example, if I have a square of side 5 and I remove a square of side 2, the remaining area is 5 squared minus 2 squared, which is 21. Meaning, I can find the area of the bigger region, subtract the area of the smaller region to get the area of the in-between region. So I'm going to do exactly that here. My limits are found to be 0 to 1. Now the outer one is contributed by x, and the inner one is contributed by x squared. So I subtract these to get pi x squared minus pi x squared squared. And the integration is from 0 to 1. So this comes out to 0 to 1 integration pi x squared dx minus 0 to 1 pi x to the 4 dx. This becomes pi x cubed over 3, 0 to 1 minus pi x to the 5 over 5, 0 to 1. That's pi over 3 minus pi over 5, which gives me a 15 and a 2 pi. So that is the volume. So the two key concepts here, A, finding intersection point, and B, realizing that because it's a region that's been rotated and not a single curve, it's not an area enclosed by a curve. It's the volume that's enclosed by, it's a volume created by the area or the region enclosed by curves. So you have to subtract the missing part in between. Now there is another variation to this particular problem, and which is rotation about other lines. And now in the same example as before, instead of rotating it about the y-axis, we're going to rotate it about the line y equals 2. So we have the same idea or the same setup. We have this graph from x equals 0, x equals 1, and that's y equals 1. Now we're saying that instead of rotating it along the y-axis, we're going to rotate it on the y equals 2 axis. Now what that means is we're still going to have, like, the slice is still going to look like a donut or a washer, but this is going to be y equals 2. And this is my x-axis, say over here. Now the difference that's going to happen is that the outer radius is now going to be 2 minus x squared, and the inner radius is going to be 2 minus x. That is the only difference that we have here. And then we still apply the same formula, 0 to 1 pi of 2 minus x squared squared minus 2 minus x squared dx. If you file this out, this comes out to pi 0 to 1 x to the 4 minus 4x squared plus 4 minus x squared minus 4x plus 4 dx by 0 to 1 x to the 4 minus 4x squared plus 4x dx, which further becomes pi x to the 5 over 5, 5x cubed over 3, 4x squared over 2, 0 to 1, 0 to 1, 0 to 1, which is pi 1/5 minus 5/3 plus 2, which equals 15. That's 3 minus 15, or wait, it's 25 plus 30 and a pi outside. So that's 33 minus 25, which is 8. So this is 8 pi over 15. That's going to be the volume. Let's look at a last example. Now, there's a solid with a circular base, and what's happening here is that the parallel cross sections perpendicular to the base are equilateral triangles. You have to find the volume of the solid. So if you look at the base, this is what's happening. For every point x, that's the value of y. Because let's say the circle is x squared plus y squared equals 1. And the cross section is equilateral triangle. So in this case, when you slice, the slice gives you an equilateral triangle. An equilateral triangle has both sides as 60 and 60 degrees. And this is 60 degrees as well. And then you also know what these values of so special property for equilateral triangle is that the angle bisector is also the side bisector. So this base, the base of the triangle is 2y, which is 2 times root of 1 minus x squared. Now, height of an equilateral triangle is root 3y, which you can figure out using trigonometry. And that's going to be root 3 1 minus x squared. So that the area of the cross section, which is equilateral triangle in nature, is 1/2 times base, which is 2 1 minus x squared, times height, which is root 3 1 minus x squared, which is root 3 1 minus x squared. Now we don't have to use pi r squared here because our cross section is no longer cylindrical, it's triangular in shape. Okay. So this goes from -1 to 1, and the area is root 3 1 minus x squared dx, which gives me root 3 x from -1 to 1 minus x cubed over 3 from -1 to 1. That's a root 3 times 2 minus 1/3 2. And that's a 4 root 3 over 3. So this last example shows you that even if you have a very general shape, like something that has cross sections which are triangular or triangular in nature, you can still use the same concept in order to find the volume. So that's the end of the examples.